I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
What if the future of flight wasn't powered by a few massive engines, but by dozens of smaller ones working together like a symphony? That's the bold idea behind distributed propulsion, a breakthrough that could change how aircraft generate thrust, conserve energy, and even control their movement. For more than a century, airplanes have relied on the same formula: concentrated power. Big engines mounted under the wings or on the tail, separate from the aerodynamic structure they move. It's efficient, but as we chase cleaner skies, quieter airports, and smarter designs, that traditional setup is reaching its limits. Distributed propulsion flips this logic. Instead of 2 or 4 large engines, we place many smaller propulsors, fans, propellers, or jet modules across the wings and fuselage. Together, they shape airflow, reduce drag, boost lift, and even back up one another if something fails. It's not just adding more engines, it's merging propulsion and aerodynamics into one seamless system. Now, here's where the real science takes off. Imagine the boundary layer, that thin film of slow-moving air hugging an airplane's surface. Normally, ingestion, or BLI, small electric fans can pull in that sluggish air, energize it, and send it back out as thrust. Think of it as recycling airflow, turning aerodynamic waste into useful power. NASA's experiments show this could save 8 to 10% in fuel, a huge leap for both airlines and defense fleets. Then comes propulsion-controlled aircraft, or PCA, a concept where thrust replaces traditional control surfaces. Instead of moving ailerons or rudders, the aircraft adjusts individual motor speeds to roll, pitch, or yaw. It's like steering a plane by balancing the push from dozens of engines, faster, simpler, and with fewer moving parts. NASA's X-57 Maxwell electric aircraft is pioneering this with 12 motors along its wings, each fine-tuning the aircraft's balance in real time. Of course, electric propulsion is the beating heart of all this. Distributed electric propulsion, or DEP, uses lightweight electric motors instead of mechanical shafts. These motors are efficient, almost silent, and can be powered by batteries, fuel cells, or hybrid generators. It's the same idea driving eVTOL aircraft, electric vertical takeoff and landing air taxis, that promise quiet, emission-free city flights. But batteries alone can't yet power long-distance aircraft, which brings us to hybrid electric systems. One standout is NASA's Stark ABL design, single aft engine with boundary layer ingestion. Here, a jet engine in the tail drives generators that power multiple electric fans along the fuselage. By re-energizing the aircraft's own airflow, it can cut fuel burn by more than 10% while maintaining conventional range. Europe's EcoPulse demonstrator, a joint project by Airbus, Daher, and Safran, takes a similar approach, combining a turboprop with 6 wing-mounted electric propellers. The result? Lower drag, lower noise, and new ways to control the aircraft using differential thrust instead of moving control surfaces. Safety and reliability are major benefits too. If 1 or 2 propulsors fail, dozens of others keep working, creating a built-in redundancy traditional jets can't match. And because each unit is smaller and modular, maintenance becomes faster, cheaper, and more flexible. Noise is another major advantage. By synchronizing electric motors, engineers can tune out sound waves, cutting perceived noise by up to 15 decibels. For airports near cities, that could mean flights almost as quiet as traffic on the ground. Still, these advances face real engineering challenges. Energy density, the amount of power stored per kilogram, is still far lower in batteries than jet fuel. Thermal management and high-voltage distribution systems need to be ultra-light yet fail-safe. And flight control software must handle complex dynamics with millisecond precision, keeping the aircraft stable even with dozens of thrust vectors changing at once. NASA's Helios solar aircraft, which failed due to aeroelastic coupling, a feedback between flexibility and airflow, serves as a reminder. Even revolutionary designs must obey physics. But innovation is accelerating fast. New superconducting electric motors can carry huge currents with almost zero resistance, drastically cutting energy losses. Supercritical CO2 cycles can recycle heat to generate extra power, boosting efficiency by nearly 20%. And hybrid demonstrators like Electra's EL2 Goldfinch are already proving these concepts in flight, taking off in short distances, staying aloft longer, and consuming far less fuel. From urban air taxis to regional transports and future military UAVs, distributed propulsion is adaptable, scalable, and transformative. It doesn't just make aircraft cleaner or quieter, it rewrites how thrust and control interact. In the coming decade, as energy storage improves and smart control algorithms mature, the skies will be filled with aircraft that no longer depend on a few massive engines, but fly on the harmony of many intelligent ones. Because distributed propulsion isn't just evolution, it's the rebirth of flight itself. Thanks for watching. Subscribe, follow, or visit idsth.com for more cutting-edge defense and tech insights. See you in the next one.